Hello, everyone. This is Yan Liu and Josh Yeh from Cloudera. And in today's session, we will cover a recent community work that enables the data lineage from Apache Flink to be captured by Apache Atlas. The session will be divided into three parts, and I will be covering the first part and go through the fundamental reasons on why this work is important. Josh Yeh from Cloudera will be covering the second part and give you some technical details on how did we manage to capture those lineage data from Flink jobs. We have also prepared a very short demo to show you the results. Okay, so for whom that did not heard Apache Atlas or Apache Flink before, don't worry. Let's flashback and take a look on what is Apache Flink and Apache Atlas. For those of you who were not familiar with Apache Flink, here is a very short and generalized description of Apache Flink. So Apache Flink is a stateful computation framework over data streams. Where the data streams not just means real-time stream data, but also includes historical data where it can be treated as a special case for data streams. We have more information on this for the next slide, but let me just focus on explaining what is Apache Flink first. So there are many use cases where Apache Flink fits in, such as real-time ETL, and event-driven applications. With the help of Apache Call Site, Flink is now capable of unifying the streaming data processing and historical data processing together using just SQL. This makes Flink a viable choice for data analytic applications and data warehouse applications, such as a real-time data warehouse. So let's take a look of what is unified analytic really means in the Flink world. So every piece of data, well, physically or virtually, has several attributes on time, while no matter explicitly or implicitly attached with the data itself, just like the birthday. So for batch processing, while normally we aggregate those data into hours or days, for our downstream reporting system and ignoring the birthday of the data itself. That's okay. It worked for a few decades in data warehousing and reporting system for enterprise across the globe. However, provide near real-time analytic and insights has more than ever required by enterprise to enable them to make faster decisions with the fast-changing situation. So there are a few technologies has been designed and implemented. Apache Storm, for example, was one of the top-level projects in Apache community to tackle those situations. Well, people were thinking that real-time analytic is different than traditional analytic. And when we need to join the results from a batch job with a real-time job, the Lambda architecture was introduced. Where you have one pipeline that is doing real-time data processing and another pipeline doing historical data processing. So merging them together at the very end, it is working and very efficient if you pick the right technology to implement this Lambda architecture. While the trade-off is that you have two complete separated tech stack, and it's really hard to maintain. So is there a invisible boundary between real-time analytics semantics and batch analytics semantics that forces us to use separate pipeline to process? Well, it turns out that there were no such thing actually. So historical data processing, also known as bounded data analytic, were just a special case of unbounded data analytic, where the bounded data analytic assumes no data will be born at the time of running this workload. An unbounded data analytic, always aware and be able to handle newly born data at the time of running this workload. That's what we call unified analytic. Apache Atlas, on the other hand, provide open metadata management and governance capabilities for organizations to build a catalog of their data assets, and classify and govern these assets, and provide collaboration capabilities around these data assets for data scientists, data analysis, and the governance team. Well, it automatically collects metadata for Hive, HBase, Spark, and Impala out of the box. Well, you can also implement your own metadata collector by extending the framework. Well, although it is a Apache open source project, it has dependencies on Apache Kafka, Apache HBase, and Apache Solr. Due to the nature of metadata itself, in order to provide quick search and relationships between each meta entities, Apache Atlas also used Janus Graph on top of HBase to provide a distributed graph database and keep all the relations as graphs. The most crucial capabilities for Apache Atlas is it can automatically generate a lineage graph between each asset element based on your workload running on the platform. So that governance team may track the lineage and understand where did the data came from and what would be the impact after it. As an example shown in this particular picture, one should easily understand that we had two ETL jobs running between 5 different tables. The first ETL job is collecting the data from a SFTP server and landing those data onto HDFS. The second ETL job reads the data from the landing zone and performing the data cleansing logic and write the results back to 3 different Hive tables. So without the help of lineage, it is hardly possible for one that can have this level of understanding on how the data came from and how the data were being written to. Well, Apache Atlas also has the ability to dynamically create classification tags like BII and data quality or sensitive or any other tags that you wanted, and associate those classification tags to the metadata. So it helps analysts and data scientists quickly and easily understand the dataset. While classifications can be tagged on any Atlas entity. For example, we're tagging a Hive ETL workload as data quality so that the user immediately understands that's an ETL job for data quality. The user are also being able to perform search by classification. Well, if they search by data quality, Apache Atlas will return all the entity that's been tagged with data quality. So entities can be associated with multiple classifications and enable easier discovery and security enforcements for the downstream users. Apache Atlas also has the ability to propagate the classification by lineage. So you don't need to tag your data, which are being written to another table again, as long as you have tagged the data from the source. Atlas type system allows user to define a module and create entities for the metadata object they want to manage. While typically the module captures technical attributes like name, description, or create time and number of replicas, and etc. And metadata objects are created and updated by process that's monitoring the real objects. So it is often necessary to augment technical attributes with additional attributes to capture business details that can help organize, search, and manage the metadata entities. So for example, a person from a marketing team can define a set of attributes for a campaign and add those attributes to relevant metadata objects. We see above introduction, so let's answer the question we made earlier. Why we need data management and lineage for Apache Flink, and why it's important. Well, since Apache Flink is a stateful streaming processing framework and can be used for ETL, unified analytic, or event-driven applications, we observed that many community users has already started migrating their existing batch ETL workload to Apache Flink, which makes the data warehouse always having the up-to-date data assets. There are also a number of users onboarding real-time analytic or event-driven applications with Apache Flink for new use cases. Well, those migration or adoption makes Apache Flink to play a vital part in their modern data lake architecture. So as shown in this slide, many community users has shifting their ODS layer or even the DW layer of their data warehouse from Hive towards Kafka. Well, the workload are doubled for sure, and the metadata are doubled as well. But what happened is there is no solution provided to keep track and manage your data lineage with data assets that's been touched by Apache Flink. And for data scientists, analysts, and governance team are losing their insight on those data assets as well. So to further illustrate the problem, let's look at an example. As a simple example here, in today's Flink world, you can monitor the operator inside each Flink jobs and understand what the job is doing. So suppose a data analyst want to understand how those jobs related to each other without any additional information. What the analyst needs to do is to dive into each of the Flink job and take note on what was the input and where did the output goes to, and repeat this again for the second Flink job. And if this work has been done very carefully, he or she can correlate those two Flink jobs and have a better vision on what they are doing. It is already hard enough for just two Flink jobs. It is hardly possible to understand the relations if you have hundreds of Flink jobs running on your cluster, not to mention if those source or targets are having multiple workloads writing or reading from it, such as Apache Hive or Apache Spark. So here comes the answer. With Apache Atlas help to collect the lineage and metadata from Apache Flink, a data analysis, scientist, and governance team can easily understand how those Flink jobs connected with each other and what is the impact to the downstream. They can also dive into each Flink job and visualize how this particular Flink job reading from the source and writing its output to the target. Until then, your data lake's access has now been fully tracked and searchable with Apache Atlas. And the next session, we will have Josh Yeh to introduce you the technical details on how Apache Atlas gather the lineage data from Apache Flink.
Hello, everyone. My name is Josh Yeh, a software engineer in Cloudera. I'm currently working on streaming data lineage. Prior to this project, I work on machine learning model lineage tracking, which is a similar data governance concept, but applied in a different application, or some might say different area of technical field. Before I start, I would love to share a little bit of the background story. The feature request was logged in open source community, and I believe it was partially motivated by the European Union's General Data Protection Regulation, aka GDPR, which is making effective data governance an essential business process. So let's look into the involved stack and how we stitch them together. Before we start, just in case there are audience are not familiar with the software, so I will give my much simpler version of narrative. one-liner to describe what the project are about. So just give everyone a new idea. So first of all, Apache Atlas. Atlas is essentially a graph database, which is used as a data governance framework that stores metadata for data processing logic to track the ownership or lineage. So just tracking input output of the processing and store some storage there. So Atlas is not a storage product per se. So aforementioned information is actually stored in support database, such as HBase, and indexed by Solver for performance search benefit. So the Atlas already integrate with the HDFS, Kafka, Hive, Spark, and etc. entities in there. So the upstream Jira to support is actually Atlas 3A12. Just to add the Flink entity definition, it's like a schema of the regular database. We already had it contribute to this Atlas Jira. The second piece of software is Flink. It is a streaming process framework for bound and unbound data. The upstream Jira is Flink 6757. Collects streaming application metadata with Atlas. So to integrate Atlas and Flink together, simply enable user, possibly enterprise user, to track the input-output data of the Flink job, their owner, and how different Flink jobs are connected to each other through the data they produce, which is the lineage. So this is a very strong requirement in many large corporate for security practice. So in current development, we have done so far in Cloudera, so we had integrate Flink streaming job for different connector, HDF, Kafka, HBase, Kudu, and plan to gradually support more and more Flink streaming operation. Now I'm showing my second slide, which in this slide we will dissect the Flink and Atlas integration into three big pieces. The first part is Flink entity definition in the Atlas system. So in an analogy, this is something like schema in relational database. The second part, we will discuss Flink job listener hook, which is used to monitor Flink job string graph and getting the metadata to send the lineages of string job to Atlas. And the third part is the support for connector to expose metadata. In this slide, we will dive into Flink application entity definition. So in Atlas, entity is an Atlas terminology. An entity in Atlas is a specific value or instance of a class type, and thus represent a specific metadata object in the real world. For every data and process logic that we want Atlas to track, we need to define them as an entity. So there are a rich set of predefined entities, such as HDFS file, HBase table, Hive tables, Kafka topics, and etc., which Atlas already support tracking the lineage of aforementioned entities. So simply put, we just want to create a Flink application entity definition in Atlas to complete the last piece of the puzzle for Flink and Atlas integration. So here in this slide is the current schema that we have contributed to Atlas upstream. At initial version, Flink application entity has 6 attributes, as you can see on the slide. So first is ID. This is automatic generated by Atlas. I think it's definitely in an incremental fashion. And start time, end time are both very self-explanatory. So config is a map type structure, and input output is a list, which is essentially Flink source and sink. And that's it for now. And I would like to make a note that the Flink application entities are just like database schemas will evolve over time. The entity definition is currently what we had contributed so far. In this slide, we will talk through in a high-level fashion of how Flink job listener hook is doing. So currently this part is a little bit tricky to build the Atlas hook along with upstream Flink code base. So we made a separate shaded classes so it can play nicely with Flink. The first step is configuration options. In order to allow user to specify the job listeners they want to use, we had add a new configuration called execution.job-listeners, which takes a list of job listeners factory class name that will be used to instantiate in the string execution environment. This allows user to specify customer Flink job listener hook at the runtime and continue monitor interaction between sourcing and syncing operation at the runtime. Secondly, a little modification on the pipeline job itself. So the newly introduced Flink listener interface goes a long way to providing a very good interface for our Atlas hook. However, the improved job listeners interface still has one thing missing, is to access to the job pipeline itself. When the Atlas hook logic is executed, it will create the Flink entity based on the current Flink job. So it needs to access things like source and sync as metadata when the job being submitted. So this change will expose either the execution plan or string graph object to the Atlas hook implementation. So making it easy to access sources and syncs. So let's look at the third building block of the whole project, connector supports. The secret sauce to the whole implementation is the logic of getting source and syncing function from the string graph. So in order for the Flink Atlas hook to get the metadata of the streaming, sync, and sourcing connector, it requires connector itself to expose the properties. Once connector exposes the property, the Flink job hook can easily access the information and construct the lineage and push to the Atlas. We had to modify the following connector to get metadata from, and which is also conforming the earlier Flink Atlas entity definition. So the first and foremost one is the Kafka topic, and also HDFS files, HBase tables, Kudu tables. The list of connects will be growing in the future. So once job listener hook acquire the metadata from connectors, the connector check the type of source it is, what kind of support so far, and create the entity accordingly. At this point, it's worth noting that Atlas already comes with a rich set entities. So once we glue all this work together, Flink rich connecting support with some modification of metadata exposure, and combined with Atlas already very rich entity definition, we can build streaming job data lineage easily in Atlas. Now we kind of skim through the three building blocks together. Next slide, we will check a zoo type architecture overview for all things that glue together to alleviate everyone's eye constraint from looking at a wall of text. So now we are looking into the architectural overview of how this integration looks like. With the Flink scroll right in the middle, left part represent a list of the sync and source connector Flink support. The right part of the graph is the destination where it gets stored streaming job lineage. The sequence works like this. First, user will launch a Flink job with a registered job listener class through a Flink configuration. This is illustrated at the right in the middle of the slide in a blue background, rectangular call out. That's where our listener hook is. When the job starts running, through Flink sync and source function, we will be able to get the metadata of the connector we support. Then, the job listener hook will construct the lineage information and push to the right side of the graph, which is a Kafka topic that has named by default Atlas hook. In the last operation, Atlas will receive the metadata information in the JSON format in Atlas hook topic. So now let's look into the examples from the Atlas UI. So right now we are looking at Kafka topic lineage. The screenshot represents a perfect lineage of a streaming job. First on the left is a data generator produce a random data pushed into a Kafka topic called transaction log. Then going through a third icon, which is a transformation job. Lastly, push into a fourth icon, which is the ephemeral Kafka topic called query output.1. I will also going through a little deep dive on the work of getting Kafka connected property. To create a Kafka topic entity, the job listener hook needs the following attribute. First, Kafka properties. Second, the topic names. Expose the property is straightforward for both source and sinks. The topic, however, is a little bit tricky. For the source, every consumed topic or pattern should have its own entity. We can simply impose the Kafka topic descriptor here. For the sink, this is a tricky part, as the topic extraction can be dynamic. Handling the dynamic topic is beyond the scope in the initial version we plan to support, as it requires continuous monitoring and update to the Atlas, which might produce a little bit performance overhead. But so far, our implementations support user control static sinks. And we also add a get topic descriptor function to the Kafka sink, where by default it will return the descriptor for the default topic. Now we are looking at HDFS as source and sink example. I used the basic work on streaming job to produce this graph. So as you can see, the first element on the left is the input file in HDFS. The second element on the right is the output file. It's also stored HDFS. So now we have every information we need for this integration project. So let's go through the deployment practice. Since Atlas is mostly used for governance purpose, the common deployment scenarios associated with enterprise-grade security. The hook itself needs to communicate with Atlas via a predefined Kafka topic called Atlas hook. So in production environment, the Kafka cluster should have been secured by one or more of the following security-related mechanics, which is authenticated by Kerberos, encryption by TLS, and authorized by Ranger. So from Flink's standpoint, the Flink Atlas hook pushing the data to Atlas hook is just as simple as pushing a regular secure Kafka topic. There's nothing special needs to be taken care of. So let's summarize the important talking point of the Flink and Atlas integration project. So the goal was for Atlas to provide the clarity of Flink jobs. So the workflow we took is a launch Flink job with a customized job listener class, which is responsible for collecting operators and or connector data and pushing to a predefined Kafka topic, which is called Atlas hook. So the end result is we make Atlas as a central repository to audit Flink job for its lineage relationship. The metadata is stored in HBase and indexed by Solars for the search performance benefit. So this is the end of my talk. I hope that you enjoy. Thank you for listening.